Good morning, students. This is Dr. Sharma, Professor, BVC Engineering College, Autonomous. Today we'll discuss about digital signal processing. So what is a digital signal processing? Before going to start about the digital signal processing, what is the overview of this digital signal processing? Digital signal processing system, analog to digital conversions, Nyquist-Shannon sampling theorem, aliasing, sampling effects in time domain, sampling effects in frequency domain, anti-aliasing filter, undersampling, sampling of band-limited signals, oversampling, and digital to analog conversion. Digital signal processing of a signal facilitates the sharing of a single processor among a number of signals by time sharing. This reduces the processing cost per signal. So, from that, we may define that the digital signal processing, first of all, the input signal, what is to be given to the any analog signal processor, that signal should be the analog input signal x of t. Here x of t is represents in the time domain, and the signal which is to be given to the analog processor, then we may get the analog output signal y of t with respect to that. Suppose, for example, while you are going for the digital signal processing, the analog signal which is to be given as an input to the digital signal processor, first of all, the analog input signal is to be converting into the digital by using the device called the A to D converter. And the output of this A to D converter is to be given to the digital signal processor, and the digital signal processor processes, or it performs the particular task based on the given instruction. That is again the result which is to be given to the D to A converter. Why? Because means the output is to be the digital in the form. So the digital signal is to be converting into the analog signal. So the input and output signal both are to be the analog signal. Meanwhile, the process is to be carried in the form of digital. While we are going for the typical digital signal processing system, it consisting of different blocks. One is analog filter, ADC, DSP, DAC, reconstruction filter. So the analog input signal which is to be given to the analog filter, and that analog filter is the band limited signal which is to be obtained, that is to be given to the analog to digital converter. So here the analog signal is to be converting into the digital form. The digital input is to be given to the DSP processor. Why? Because my DSP process only accepts the digital signals. So the DSP, after getting the input from the ADC converter, the DSP processor performs that particular task and the process that signal, and then that is to be given to the DAC converter. Why? Because the output which is to be the digital in form, that is to be again converting into the analog signal, but the output signal which is again to be reconstructed by using the reconstruction filter, and the analog output which is to be obtained. So from that we may say that it consisting of an analog filter called as anti-imaging filter, A to D conversion unit, and a digital signal processor, and a digital to analog conversion unit, and an analog filter called reconstruction filter or anti-imaging filter. So this is the total typical digital signal processing system. So the analog signal which is to be given to the filter, that filter is to be called as an anti-aliasing filter. What is an aliasing? That what we may discuss it later. So the analog and anti-aliasing filter, the output of the anti-aliasing filter is to be given to the analog to digital conversion, and the signal which is to be formed in the form of digital codes. The digital codes are to be supplied or given to the digital signal processing based on that instructions by the user. It processes the particular task, and then the output is to be obtained in the digital form. Again, that is to be converting into the D2A converter, that means the digital to analog converter, and then that is to be given to the anti-imaging filter for reconstruction, and then the analog signal which is to be obtained. So this is the step by step process what we are discussing. So the analog signal, how that analog signal is to be converting into the digital. So the analog signal is to be converting into the digital by using the theorem called sampling theorem, as we are already know that. So the samples of this analog signal is to be obtained here, and that is to be given to the sample and hold circuit, and then the output of the sample and hold circuit is to be given to the quantization and digitization for converting of this analog input signal and discrete signals. Why? Because means the analog signal is to be sampled, then means you may get the discrete signal. The discrete signal again quantized or digitized by using the A to D converter with that outputs of this quantization or the digitization is to be given to the digital signal processor. So the input for the digital signal processor is in the form of digital codes, and then process is to be carried on, and the digital codes again to be converting into the analog level, and then zero order and hold circuit is to be given, and there you are using the smoothing function, and then you may get the analog. So this is about the reconstruction filter stage. So analog signal is to be given to the A to D converter, A to D converter to the DSP processor, DSP processor to the D2A converter, and again analog signal. So the input and output for both are to be the analog in nature. So while you are going for the analog to digital conversion, most of the signals of practical interest are analog in nature, like voice, video, radar signals, transducer, sensor outputs, or biological signal. So in order to utilize these benefits, we need to convert our analog signals into the digital. So this process is to be called as A to D conversion. So for A to D conversion, there are three steps process is to be there. So suppose for example, if the analog signal is of XA of t, that is to be given to the sampler, then you may get that analog signal is to be converting into the discrete time signal in the form of some x of n. Here n is nothing but the number of sequences. So the analog signal is to be converting into the discrete time signal, and then it is to be given to the quantizer. So the output of this quantizer is nothing but the quantizer signal, that is nothing but xq of n, and that is to be given to the A to D converter. This quantizer signal is to be converting into some digital form in the form of 0 1 format. So what are the three steps we have followed here? First one is sampling. Conversion from continuous time or a continuous valued signal to a discrete time or a continuous valued signal. Second stage is nothing but quantization. So conversion from the discrete time to continuous valued signal to the discrete time and discrete valued signal. The third one is coder. This is nothing but the digital coder conversion. So coding conversion from a discrete time to discrete valued signal to an efficient digital data format. These are the three steps which are to be involved in the analog to digital conversion. This is the first stage before applying to the DSP processor. So, sample and hold circuit. An analog signal is continuous in time and continuous in amplitude. It means that it carries an infinite information of time and infinite information of amplitude. So, the analog signal has some value definite at every time instant. So, it has an infinite number of sample points. So, sampler and hold circuit, it is impossible to digitize an infinite number of points. So, after conversion of an analog signal into the discrete signal by using the sampling theorem, there infinite number of sampling points are to be there that are impossible to digitize. So by using some conversion techniques are to be used for converting of that discretized signal into the digital signal. So the infinite points cannot be processed by the digital signal processor or a computer, since they require an infinite amount of memory and infinite amount of processing power for computation. So sampling is the process to reduce the time information or the sample points. The first essential step in analog to digital conversion is sample an analog signal. This step is performed by sample and hold circuit, and which samples at a regular intervals called as sampling intervals. And the sampling can take samples at a fixed time interval. The length of the sampling interval is the same as the sampling period, and the reciprocal of the sampling period is the sampling frequency Fs. So, after a brief acquisition time during which a sample is acquired, the sample and hold circuit holds the sample steady for the remainder of the sampling interval. The hold time is needed to allow time for an A to D converter to generate a digital code that best corresponds to the analog signal. So the analog signal what is to be sampled discretized after getting the sampling points or after getting the sampling intervals, that is to be digitalized here. So if x of t is the input to the sampler, the output is x of nt, where t is the called as a sampling interval or a sampling period. After sampling, the signal is called discrete time continuous signal. So whenever a time continuous signal or an analog signal is to be discretized, it is discrete in time, but it is a continuous signal. So the discrete in time and continuous in amplitude. So suppose for example, if we see here, this is an analog signal and sampled by every zero point 0.1 millisecond, then automatically it is also to be just like as a input signal, but it has a discrete instance of time. And after that, suppose if we sampled at every 1 second, it is to be called as a this is to be called as a sampling period, and this is to be the sample every 1 microsecond. These are the different types of diagrams which are to be used for, or which are to be used, or which are to be knowing for the process, how the process is to be carried on. So figure below shows that an analog signal which is to be definite at an interval every point over the time axis. So this is about an input signal, and it is to be converting into some samples like 0t, 2t, 3t, 4t, up to that n of t. N is nothing but the number of sequences, number of sampling periods. So the distance between the two successive samples is to be called as the sampling interval, and the analog signal is a continuous time signal. And then we are to be whole. Each sample maintains its voltage level during that. The starting point is to be taken into the consideration. So from that we may call that one as with respect to the sample and hold analog voltage for ADC. This process is to be called as sampling and hold process. So the sample signal is to be converting into digital in form. So the sampling theorem guarantees that. What is a sampling theorem? Where from first onwards we are saying that sampling theorem, sampling theorem. So what is a sampling theorem? A sampling theorem is it must satisfy this condition: fx is greater than or equal to 2fm. So the sampling theorem guarantees that an analog signal can be perfectly recovered as long as the sampling rate is at least twice as large as the highest frequency component of the analog signal to be sampled. This is called as the sampling theorem condition, which is to be proposed by Shannon. That's why it is to be called a Nyquist-Shannon sampling theorem. This one is to be called as Nyquist rate. So suppose for example, if we discuss some example here, for a given time of sampling interval t, which is defined as the time span between the two sampling points, the sampling rate is therefore given by Fs is equal to 1 by t samples per second. Suppose for example, if the sampling period is to be given as 125 microseconds, so what is the sampling frequency? Fs is equal to 1 by t. T here what? 125 microseconds. So 1 by 125 microseconds is equal to 8000 samples per second. It is to be in the form of hertz. Why? Because this frequency we are measuring that one as in the form of hertz. Like that only, take one more example. In order to sample a voice signal containing a frequencies up to 4 kilohertz. Here the frequency is given. We need a sampling rate 2 into 4 kilohertz. Kilohertz means 1000. So 4000. That is equal to 8000 samples. How many samples for a 4 kilohertz of frequency voice signal? It consisting of 8000 samples per a second. And similarly, for the sampling sound with the frequencies up to 20 kilohertz, we may multiply that with respect to that. So 2 into that frequency, which is equal to 40,000 samples per second. And suppose for example, if we take one more example, for the following analog signal, find the Nyquist sampling rate and determine the digital signal frequency and the digital signal. X of t is equal to 3 cos 70 pi of t. So the maximum frequency component is x of t. So f max is equal to 70 pi by 2 pi. Why? Because this is a 2 pi signal. So that is equal to 35 Hz. Thus the maximum frequency is 35 Hz. Therefore, according to the Nyquist, we need a sampling rate of Fs is equal to 2f max. 2 into f is nothing but 35. 2 into 35, that is equal to 70 Hz. So the digital signal which should be have the frequency that is equal to 2 pi into 35 by 70, that is equal to pi. So the digital signal can be represented as x of n is equal to 3 cos pi n. Okay, this is one more example. And let's discuss about another example for learning about this. So find the sampling frequency of the following signal. S of t is equal to 3 cos 50 pi t plus 10 sin 300 pi t minus cos 100 pi t. So S of t is equal to 3 cos 50 pi t plus 10 sin 300 pi t minus cos 100 pi t. Here there are three different frequencies are to be given. With respect to that, we may find out the frequency from the previous formulas what we have discussed here. So with respect to that, what is the maximum frequency here? So if we observe simply which one is the highest, that's for 300. So with respect to that, it is the maximum frequency. So the sampling frequency should be Fs is greater than 300 Hz. So from this we discussed about that how an analog signal is to be converting into the digital signal, and in the next we'll discuss about the remaining concepts like aliasing and D2A conversions and etc. further videos.